Hi folks, this is Calc 3 Quiz 14. We're asked to set up a double iterated integral to find the volume of a solid. The solid is being bounded by two surfaces. We have z equals x squared plus y squared, which we're told is a paraboloid. And we're given a surface z equals 4x, which we're told is a plane. Hopefully we don't need to be told those things. We know them. So let's try to sketch what's going on here. If I look at the traces in the zx plane and zy plane and look at level curves, I get my nice friendly paraboloid. What's going on here with z equals 4x? Well, sometimes when trying to visualize things, if it is just two variables involved here, it might help to just draw what's going on in the zx plane. In the xz plane, z equals 4x is a very steep straight line. It's coming up like this. Now, if I were to graph this on the 3 dimensions, what I have to remember is that y is a free variable. So if I try to visualize what's going on, I'm going to have this steep line coming up this way and going back into the blackboard. But since the y is free, I'm going to have the freedom to swish left and right. To try to get a better idea of the relationship between the paraboloid and the plane, let's go ahead and sketch the zx trace of the paraboloid, z equals x squared, and you'll see I get that. So there in fact is going to be some area in the zx plane that's bounded by both curves. That's going to translate to slicing off a part of this paraboloid. So we can try to sketch it. It's going to come up from the origin and it's going to poke through. So I'm going to try to shade this. But since the y is free, I have freedom to move left and right. So it's going to be slicing off a patch of this paraboloid. Alright, so I know that's difficult to see, but where the geometry leaves off, hopefully the algebra will pick up. So if we were trying to find the area between two curves in Calc 1, we would find the intersection of the two curves. So in Calc 3, we're going to find the intersection of the two surfaces. So to find where these guys intersect, I'm going to set them equal to each other here. I get x squared plus y squared equals 4x. I recognize that as being a conic section. If I subtract the 4x over and complete the square, I see that the points of intersection on these two surfaces, their x and y coordinates are related by this equation. This is a circle centered at 2, 0 with a radius of 2. So that's the relationship between x and y for the points that are on both surfaces. In other words, if I took the boundary of this solid and projected it down to the xy plane, I'm getting that. So as we've seen before, this is a good candidate then for the base of this solid. What does this look like here on this picture? Well, the x coordinates go from 0 to 4. So that would be like having it in here. So we can imagine we have a two-dimensional cross-section of what's going on. We're going to have the base then being the xy plane, which means the height variable is going to be governed by the z. And we can see exactly what the height is going to be. Right, we have the bottom curve, which is the paraboloid. We have the top curve, which is the plane. So the height's going to run from here to here. So our volume then is going to be a double integral over our base times the height dA. So I'm going to call this region here R. That's the circle and everything inside it. That's the double integral over R. And for the height, we take the top minus the bottom. That's z equals 4x minus z equals x squared plus y squared dA. So that's the double integral that's going to compute the volume for us. Now to evaluate this, we need to set up this double integral. And since we have a circle that's tangent to the y-axis, polar coordinates is going to be the coordinate system of choice. So let's do that. So let's look at this bounding curve, x minus 2 squared plus y squared equals 4. And let's switch it over to polar. So to switch over to polar, we have two primary substitutions. X is r cosine theta, y is r sine theta. If I make those substitutions, I get r cosine theta minus 2 squared plus r sine theta squared equals 4. We expand this out, we get r squared cosine squared theta minus 4r cosine theta plus 4 plus r squared sine squared theta equals 4. I get some Pythagorean magic happening here. R squared cosine squared theta plus r squared sine squared theta. That's just r squared. I have minus 4r cosine theta. And these 4's cancel out. I can factor an r out. And I got either r is 0 or r is 4 cosine theta. Well, when theta equals pi over 2, I get r equals 0, so this is really the polar coordinate conversion for that curve. Now, if I want to graph this, r equals 4 cosine theta, I can use the techniques we developed in Calc 2. I guess I'll do that up here. I would look at y equal 4 cosine x, and I haven't messed with the x at all, so the period is still 0 to 2 pi, so these are the quarter marks, 2 pi, 3 pi over 2, pi, pi over 2. I'm going to graph this in blue. So at 0 we're up at 4. Pi over 2 we're at 0. Pi we're down at negative 4. 3 pi over 2 we're at 0. 2 pi we're up at 4. So we get our nice little cosine curve. Same period as before, but it's got an amplitude of 4. So if I'm going to trace this out then, I start at 0, 4. So when theta is 0, the r is 4. So when theta is 0, I'm going to be out 4 units. And as theta runs from 0 to pi over 2, the r goes from 4 down to 0. So that's how in Calc 2 we indicate it this way. So that's, the radius is shrinking as we come into the pole. So it's going to come in like that. Then from pi over 2 to pi, the radius turns negative. So instead of plotting over here, we plot over here because the radius is negative, so it's just going to continue this thing around back up to here. So what this tells us is that for theta between 0 and pi, that's all it takes to sweep out one time around this circle. You can go ahead and double check it. As you go from pi to 3 pi over 2, you're going to be retracing this part. From 3 pi over 2 to 2 pi, you're going to be retracing the bottom. So this is important to know.